Check it out now, y'all.
nanoHUB-U online instruction.
This is the second lecture of week 5. Today we're going to start putting all the pieces together that we have been discussing on the previous weeks. The first model that we're going to be discussing is the reaction zone model. Okay, this model was published by John Newman at the end of the 1990s. Okay, and it really gives us an opportunity to understand how people are trying to abstract and describe how batteries behave in the limit of materials where the conductivity, basically the ohmic drops, are the limiting rate for specifying the performance of a cell. Okay, and to justify the topic, I'm going to start by showing you a voltage versus capacity plot. And well, here, as we have learned already, each curve you can see here is labeled based on the C rate that this cell will have. Okay, this one corresponds specifically to a graphite lithium manganese oxide cell at 25 degrees C. In this case, 1C, basically the C rate at which a battery discharges in 1 hour, right, corresponds to 2 milliamps per centimeter square. Okay, 1C, you can see here, a battery that discharges in 1 hour, right, corresponds to this plot over here, and you can see 2C, which is 30 minutes, 4C, which is 15 minutes, and so on and so forth, right? We discussed this plot already in past weeks. Okay, you can see different models. Well, in this case, the model, which corresponds to the line, and the experimental data, which corresponds to the symbols. This is extracted directly from Mark Doyle's thesis, a student from John Newman, as Mark was in this case trying to validate his model to describe lithium-ion batteries. And I want you to notice something here very interesting. This battery that discharges, this point C discharge battery, notice how it's following, it's delivering us a relatively large voltage. Okay, and if instead I discharge that battery at 1C, notice that even on this, this axis, you can think of it as a normalized time. At the very beginning, say at t equals 0, just from instantaneously extracting a current from the battery, okay, we have a vertical ohmic drop, okay, and then we have a shape that follows very closely the 0.2 C rate, it follows it in parallel until it drops. You can see that this is the loss, right? Basically, this is the charge that we could not use with respect to the 0.2 C, okay, and you can see as the C rate increases, that vertical ohmic drop keeps increasing linearly with the voltage, okay, with the current, okay, and that voltage drop should be proportional to the internal ohmic losses in the cell, okay, and in this case, well, for 7C, the voltage drop is so high that if your cutoff voltage were 3 volts, basically you wouldn't be able to use the cell beyond 5C really, and for a very short period of time, and your losses will correspond to the contributions from the voltage, the material potential equilibrium response subtracted with all the ohmic contributions. We have learned that those contributions are a result of the transport across the electrolyte, the porosity and associated tortuosity, the interfacial reactions as they occur, reversible and irreversible. And we would like to capture this without trying to make anything very complicated. Basically, we're just trying to understand physically what happens in the system. Okay, so this slide corresponds to basically the microstructure of a battery as reported by Quinn Horn and published in a paper by Christensen. And in this case, the cathode is such that lithium is coming from this side. Okay, and in this case, the particles are lithiating and dilithiating after several cycles. And what you can see here is that the particles that are closer to the anode have gone through so much electrochemical work that at some point they just broke into pieces. Okay, suggesting with this that really reaction is occurring in one region. Basically, that there's a zone. Think of it as that there's some sort of like reaction zone where the bulk of the reaction took place, bulk of the charge being intercalated is. Notice how the back of the electrode really is pristine, is still clean, suggesting that really all the work was performed here. Okay, really what we're saying here is that from the entirety of unreacted material at the beginning of the discharge, only one fraction, this fraction over here, was effectively being used. So during discharge, basically this boundary moved as charge was being intercalated until we reach its end, especially if it occurs at a high C rate, and then when you recharge it, basically it went backwards, right? It went in the opposite direction. So really, what we're trying to do here is trying to find a rationale as to how the lithium ions, as they are diffusing through the different particles, basically end up finding a spot where the reaction takes place, while the electrons, as they are percolating between the particles and even through the particles, in this case through the conductive carbon, manage to find that spot. And in this case, this distance is something that the lithium ions will have to traverse, while this distance over here is the distance that the electrons have to traverse in order for the reaction to take place wherever you have a spot available. Obviously, because the lithium ions are the heaviest, they will take the longest time to pass, and in comparison, as long as there is a contact between the in the conductive carbon from the back contact, you can transport those electrons for that reaction to take place. Now, this model is referred to as Newman's reaction zone model. You can think of it as trying to resolve the microstructure, or instead, just like Newman did, you can think of instead of the equivalent circuit of the system. And in this case, you can think of it as a charged cell being a set of little capacitors, right? Like each sliver of battery material is a place where you can store that charge. And once you have used one of these capacitors, we can remove it from the system, and instead the ions have to traverse the ohmic obstacles imposed by the microstructure to reach the next layer, in this case the next capacitor, and we store it there, remove it from the system when it's stored. Basically, what we're saying here is that the boundary moves, and as that boundary moves, we basically are opening this part of the circuit, leaving only this resistance that will increase the ohmic loss as the reaction proceeds. And this boundary basically will be the interface, or our conceptual interface, between what we have used from the cell and what still can be utilized. Okay? How far will we go? Well, depends on how large these losses are as the battery is discharged, and how fast this boundary meets the end before, and when that happens, of course, the voltage will drop to a value of below the cutoff voltage, and we cannot use it. So really, what part the system has? Well, we can talk about the losses that occur through the separator. This is basically an inactive material. Basically, all this does is oppose, the separator just opposes a specific loss, and we have talked about the structure of these systems already, right? We have this distance x of r, which you can think of it as the spot where the reaction is dominating the system. We call that x of r, the reaction zone, okay? And we of course have the unreacted material, and we would like to account for how much charge is coming through here, how much charge is being consumed, and how that relates to the speed of that interface, okay? So that's what we want to account for, that's what we want to describe, and if we catch that, we should be able to relate that to the losses occurring here as the reaction proceeds, okay? So, well, just to get started on this, think of that at t equals 0, what you have is that, well, basically you have that if at all, you have no loss occurring in the system at t equals 0, and to put the other extreme of the system, at the end of the discharge, we have reached an instance called TD, which think of it as the discharge time, and by that time either we have reached all the way to this end, or we have reached basically the cutoff voltage, okay? That's the instant that we want to include. How does this work? Physically, what's going on, you can think of it as the amount of total volume that we have, okay, corresponds to the thickness that has been utilized, okay, times the current density, okay, times, so I'm sorry, you have the thickness that you have utilized times the charge, okay, modulated by the porosity. If you think about it, the more porous the system is, the less charge you will be able to utilize. And that should be equal to the amount of current that is going through the separator times the time, right? Because on this end, current times time gives you the charge, and that should correspond to the total charge that you use, which is related to, in this case, to the porosity of the system and how much thickness you have utilized. Okay? That mathematically we can express it by saying effectively that the thickness of utilized material, in this case the reaction zone, corresponds to the amount of charge that we have effectively used, okay? Which, if you think about it, if the porosity is the amount of material that we're not using, and then 1 minus epsilon corresponds to the porosity, to the region, of the amount of material that we have actually used, okay? And this basically has units of charge per unit area, because in this case Q corresponds to the amount of charge per unit volume that we have, and then that corresponds to, if we have I being the current density, in this case in coulombs per meter square per second, when we multiply it by time, gives us amount of coulombs per meter square. So from there we can then solve for the reaction zone as being proportional to the current density, the elapsed time, and how much charge we can store. Basically, the solubility limit of our cell is hidden here, and the porosity, you can see, is directly related to it. So you can see how the wider the compositional distance where we can put lithium in, the more lithium we can store, the slower this reaction zone will move, because we will have to basically consume more charge, okay, in order to move that boundary further. And in this case, or we will have to apply a larger current in order to extract that charge. Okay. Now, how does this relate to the voltage of the cell? Well, that becomes very straightforward. Okay. Basically, what we want is to have the total voltage of the cell to be the equilibrium potential as we derived it and discussed it a few weeks back. Okay, and subtract all the ohmic losses, in this case the loss due to the separator, okay, minus the loss from the distance of reacted material, basically the reaction zone, as this boundary is moving to the end of the cell. Okay, so in this case that loss is proportional obviously to the current, okay, times the thickness of the region, in this case this is the thickness of the separator, divided by the conductivity of the separator, okay, plus the other loss is the reaction zone length, okay, divided by the conductivity, the effective conductivity of the porous reacted layer, okay. That's what we would put in here, okay. And so that's why we get these two losses. You can put more losses, of course. You can put losses of the back contacts. You could put the losses also of the electrons as they go through the unreacted material, which will be also, of course, related to the reaction zone length. But in this case, if I have a thickness of the separator of the cathode to be h sub c, you would have to subtract from h sub c this distance, and it's something that you would add, that would just subtract on this corner, right, on this additional length. Okay, so if you do that and you make the substitution, okay, basically what you will get is the constant loss, constant in the sense that it's only proportional to the current of the thickness of the separator and the conductivity, the effective conductivity of the separator. As we know, that separator itself has its own tortuosity, okay, and has its own porosity, and that's why you want to make your separator as thin as possible, okay, without, of course, allowing for losses when you are not discharging it. Here you can see I squared T over 1 minus epsilon times Q. That basically corresponds to that I times X of R, which is what we had before, right? You can see it here. Now we have, if before we had a current, by multiplying with this other current, we have an I squared term. It's proportional to time, meaning the loss will increase linearly with time. And that shouldn't surprise us now, because this distance is increasing linearly as time progresses. But what was put here, that kappa, that conductivity of the layer, really is, in this case, is modulated by the porosity of the system. If you remember, right, the effective conductivity of the electrode in the Brougeman limit, in the case of where the Brougeman approximation applies, corresponds to the conductivity of the electrolyte, okay, times the porosity divided by the tortuosity. And if the tortuosity goes as 1 over epsilon to the 1/2, we end up with this relationship over here. So you can see how it becomes then a nonlinear problem as to what is the effect of porosity on the losses. Obviously, if I have no porosity, then my losses skyrocket. And if my porosity is 100%, also, well, I don't have any material to react, so this equation stops valid. So clearly, this shows that the losses reach some extremum value between 0 and 1, and that gives us the opportunity to optimize how the cell behaves. So if you use the potential, say for lithium manganese oxide, okay, directly, you will see how, depending on what type of electrolyte you use, right? And we discussed this at the beginning of the week, right? Where we were saying that we have different types of electrolytes, different types of salts. You can basically control the slope of this loss, okay? By controlling that. This linear contribution to the separator will give us this vertical drop that will occur here too, okay? But it will be increasing linearly as time proceeds. Okay, and notice how it will become a quadratic with current. So what you find here then is that the vertical loss based on this model really corresponds to the losses due to the separator, right? And you can see how the greater the current, the greater the loss, and at least qualitatively we get the response that this material will deserve, or this material actually expects to have. And in this case, the slope, the linear slope with respect to the equilibrium value, okay, really corresponds to the contributions from the losses associated to the electrolyte and the porosity of the system, right? So, and again, here you can, if you have that the charge that you can store in the cell is very, very large, then this slope will become flatter, okay? Or if the conductivity in this case of the material is very large as well, then it'll be flatter too. And I think you can see here how the elements of what we have discussed in previous weeks, how if we develop a battery which has a high conductivity and high charge, we will be able to deliver a larger voltage, a flatter voltage as time progresses, and how in this description, the losses as a result of the reaction, as the reaction proceeds from one extremum to the electrode to the other one, will deliver that response. And that actually gives you the opportunity to visualize the voltage capacity curve in a completely different light. Okay, because if you do that, well, what you will see is that really these different drops then correspond to internal losses as a result of the non-active components, okay? Not necessarily, of course, the separator alone. As we know, also the interfacial resistance and the other components will also contribute to this, okay? And this shape will be mainly given, okay, by the equilibrium contributions, okay? And how fast the slope comes down will depend on how much the reaction zone has moved forward. Okay, and that makes it a very interesting description and allows you to start visualizing this and try to find ways to optimize the system. Now, there are several restrictions, as to how the battery will perform. Okay, the battery will stop running if any of these constraints are being satisfied. First, if we reach the short circuit limit, basically if we apply a current, okay, that is greater than the current occurrence to the cell. Basically, all the losses are occurring because I took one extreme of the cell and basically connected to the other one. So that is how large the current would be. The other one is I have reached indeed the cutoff voltage. In other words, the moment my voltage drops below this threshold that I specified, but depends on the applications. In many applications it's referred to as the 3 voltage cutoff, in other cases 2. It really depends on the application that you want to use the cell for. Or if if the reaction zone edge x of r has reached the thickness of the cell in both the cathode or anode, right? And if that happens, if you have reached that maximal capacity, then really you should really stop using that simulation, or in this case, you have reached and fully utilized the entire charge. We specify that condition by defining TD as having reached, basically x of r has reached h sub c, and well, there's really not much to do after that. So whenever any of these three has reached, then we can call the battery to be discharged, and those are the restrictions. Assuming we have used the maximum amount of charge on that cell, okay, then we can go back and substitute that TD in here, okay? And if you notice, at least from the previous slide, you can see that that TD depends on the thickness of the electrode, and then you have everything you want here, right? Because now what you have is, and let me put it there, okay? You can go and substitute TD as a function of h sub c. So now you have an equation for the energy of the cell, okay? Completely as a function of the contributions for the different microstructural aspects, right? You have the porosity, you have the solubility limit, okay? You have the thickness of the separators, you have the equilibrium potential. So in principle, all you need to do is engineer all these different components microstructurally so that you can maximize how much energy you have. How do we come up with the expression of energy? Well, if you remember, the energy corresponds to the integral of the voltage times the charge integrated over time, and that's how you get that number, right? And if you do that, well, you know that you have the losses, the separator losses. You can see how these ones are dependent on the current that you use, and in this case of the thickness of the system, and the polarization reaction losses, right? So if you do that, what you will get is you will have a linear contribution, okay, and this term over here, a quadratic contribution for current and a cubic contribution for that, okay? So if you do that and you integrate it, what you will find is that you can definitely write an expression simply as a function of the thickness of the cell, okay, and try to optimize for the thickness given a fixed porosity, or given a fixed thickness, how would you change the porosity in order to improve that? Again, notice that if I have 100% porosity, basically if epsilon is 1, basically I don't have any energy, and if epsilon is equal 0, basically my losses are maximized. So there has to be some sweet spot there as a function of thickness. And what this slide shows is what is the energy that the battery delivers. You can see in watt-hours per meter square, okay, as a function of thickness of the cell, okay, and how, in this case, let's start, for example, at a low porosity value. So you can see how at epsilon equals 0.4, you know, as I make my electrode thicker, I start gaining on energy. Then the ohmic losses, because of you're imposing a thicker distance that the ions have to go through, increases, and then instead of even extracting energy, I will actually start losing energy at some point. If I change my porosity instead, basically to open up some spaces from 0.4 to 0.5, I have the same trend, except that now, because I have additional paths for ions to go through, I reach a higher value, and how, as I keep changing my porosity, that maximum changes, and if I go, and you can see from 0.6 to 0.7, how that maximum then starts to come down again. I can make my cell last longer as the porosity increases. My losses as a result of the transport of ions through the percolating paths decrease as I increase the porosity, but the amount of energy will just keep coming further down. So clearly there is an optimal thickness and an optimal porosity beyond at which we will be able to maximize that energy density. And if you look at the previous slide and try to use those values of that equation of the energy density as a function of porosity and thickness, you can optimize that electrode in the absence of diffusion limitations. So if you do that, okay, we can find those optimal values, and it becomes a very straightforward approach. Simply, you just take the derivatives, the partial derivatives with respect to these parameters, and try to find the extrema, and then substitute it back, and you will find that the optimal thickness really ends up being a function of the porosity, the separator, and the current that you use. This is important because it means that in the absence of diffusion limitations, where only the ohmic losses are dominating the transport of the cell, what really controls the system, the optimal thickness, will depend the current, the power density that you're extracting from your application. That's all depends on, okay? So that means that you cannot optimize a battery, the thickness, the microstructure of a battery, for all the applications, but you have to be very conscious of what the power density, what the current density of that application is, to be able to specify the thickness of the electrode. And away from that, the microstructure, your cell, will be suboptimal. Okay? If you find, now, once you have found that optimal thickness, you can go back, take that thickness, and find what the optimal porosity is. And you can do this analytically, and you will find that actually the optimal porosity corresponds to 3/5 or 0.6, okay? Really, you can see here that in the absence of diffusion limitations, only, again, and I have to say this several times so that it's very clear, that in the limit of diffusion limitations, you really you have to throw away 60% of the charge that you could store in the material just to open spaces for lithium to transport, so that you can maximize the energy density, so that you can use the high conductivity of the electrolyte to maximize your cell. And notice how that thickness will increase if I increase the conductivity of the electrolyte, and it's not going to be the same to use an organic electrolyte than to use a ceramic electrolyte, because of the material limitations of each of them, and how you want to make your separator as thin as possible to do that, and that will specify what will be the thickness of the electrode. And notice that if you satisfy that, then the optimal porosity will be 0.6, okay, for this relationship. Now, if instead we're limited by what the cutoff voltage limit is, basically if we assume that the voltage has to reach a voltage of phi naught, then we can indeed find what the discharge time is, okay, and if we have that discharge time well specified, then what you will find is that then you can solve for what the energy density is as a function of that. And notice that how much energy you're going to store is going to really depend on what the cutoff voltage is, and the same rules apply. You can see how the energy density will be greater the greater the conductivity of the electrolyte, and your relationship for the porosity will still be the same. Okay, so and that's on that end. How does the separator put any constraints on this? In this case, here we're looking at the energy density for different separators, and you can see how as you go from 0.4, 0.5, 0.6, basically as the separator becomes, as the battery becomes more porous and more porous, the losses will start dropping, being the maximum obviously at 0.6. Okay, and at some point, if the separator is too thick, okay, it doesn't matter what you do, you will get no energy out of that battery. Okay, so that becomes important. So definitely there is a cutoff separator thickness that you have to go through. Basically, there is this critical value H sub S that you will have to get in order to get something out of that. And why? Because beyond that number, basically you won't get any response at all. Now, what are those optimal values then for the optimal separator thickness? Okay, you will the minimum will be basically given by the short circuit. Okay, and another one will be given by again, it's highly dependent on what current and density is and what your cutoff voltage is. So if we summarize all of this, okay, really what we're saying here is that really the optimal separator thickness will be given by the thickness of the different layers, in this case of the separator, and an optimal porosity for the system. And in this case, we're assuming always that the reaction zone always reaches the end, right? If you have some phantom reaction zone where you actually go beyond the thickness, then this model is not valid anymore. And finally, for and this is very important, this model should never be used for systems that are not ohmically limited. Basically, if you want to include diffusion limitations, this model will not apply. The material potential in this case is, as you can see, state of charge independent, which is something you would have to include. Okay, the porosity of the system is time independent. Basically, if the porosity keeps expanding or contracting as a result of the intercalation, you will not be able to use that. And finally, well, and again, I really want to emphasize this: the diffusion is not relevant in this system. Okay, now I'm going to show you on the next lecture how for systems where you can ignore these diffusion limitations, you can apply ideas like this, and how people have really been trying to get rid of the diffusion limitations, and these ohmic losses, as you can see, they play a very important role. And in the next lecture, we will talk about that, because we want to be able to, ideally, or the name of the game, the holy grail on battery design, is trying to minimize those polarization losses to maximize the energy and power. Thank you.